Pulse code modulation is a method used to digitally represent sampled analog signals. It is the standard form of digital audio in computers, compact discs, digital telephony and other digital audio applications. In a PCM stream, the amplitude of the analog signal is sampled regularly at uniform intervals, and each sample is quantized to the nearest value within a range of digital steps. Linear pulse code modulation is a specific type of PCM where the quantization levels are linearly uniform. This is in contrast to PCM encodings where quantization levels vary as a function of amplitude. Though PCM is a more general term, it is often used to describe data encoded as LPCM. A PCM stream has two basic properties that determine the stream's fidelity to the original analog signal: the sampling rate, which is the number of times per second that samples are taken, and the bit depth, which determines the number of possible digital values that can be used to represent each sample. History: in the history of electrical communications, the earliest reason for sampling a signal was to interlace samples from multiple telegraphy sources, and convey them over a single telegraph cable. Telegraph time division multiplexing was conveyed as early as 1853, by the American inventor Moses G. Farmer. Electrical engineer W. M. Miner, in 1903, used an electromechanical commutator for time division multiplex of multiple telegraph signals, and also applied this technology to telephony. He obtained intelligible speech from channels sampled at a rate above 3500 a 4300 Hz. Lower rates were unsatisfactory. This was TDM, but pulse amplitude modulation rather than PCM. In 1920, the Bartlin cable picture transmission system, named after its inventors Harry G. Bartholomew and Maynard D. McFarlane, used telegraph signaling of characters punched in paper tape to send samples of images quantized to 5 levels. Whether this is considered PCM or not depends on how one interprets pulse code, but it was transmission of quantized samples. In 1926, Paul M. Rainey of Western Electric patented a facsimile machine which transmitted its signal using 5-bit PCM, encoded by an optomechanical analog to digital converter. The machine did not go into production. British engineer Alec Reeves, unaware of previous work, conceived the use of PCM for voice communication in 1937 while working for International Telephone and Telegraph in France. He described the theory and advantages, but no practical use resulted. Reeves filed for a French patent in 1938, and his U.S. patent was granted in 1943. By this time Reeves was working at the Telecommunications Research Establishment. The first transmission of speech by digital techniques was the Sixily encryption equipment used for high-level Allied communications during World War II. In 1943, the Bell Labs researchers who designed the Sixily system became aware of the use of PCM binary coding as already proposed by Alec Reeves. In 1949 for the Canadian Navy's DATAR system, Ferranti Canada built a working PCM radio system that was able to transmit digitized radar data over long distances. PCM in the late 1940s and early 1950s used a cathode ray coding tube with a plate electrode having encoding perforations. As in an oscilloscope, the beam was swept horizontally at the sample rate while the vertical deflection was controlled by the input analog signal, causing the beam to pass through higher or lower portions of the perforated plate. The plate collected or passed the beam, producing current variations in binary code, 1 bit at a time. Rather than natural binary, the grid of Goodell's later tube was perforated to produce a glitch-free gray code, and produced all bits simultaneously by using a fan beam instead of a scanning beam. In the United States, the National Inventors Hall of Fame has honored Bernard M. Oliver and Claude Shannon as the inventors of PCM, as described in Communications System Employing Pulse Code Modulation, U.S. Patent 2,801,281 filed in 1946 and 1952, granted in 1956. Another patent by the same title was filed by John O. Pierce in 1945, and issued in 1948, U.S. Patent 2,437,707. The three of them published The Philosophy of PCM in 1948. Pcm was used in Japan by Denon in 1972 for the mastering and production of analog phonograph records, using a 2-inch quadriplex format video recorder for the digital signal, but this was never intended to be a consumer product. Implementations: Pcm is the method of encoding generally used for uncompressed audio, although there are other methods such as pulse density modulation. The 4ESS switch introduced the first time division switching system in the US in 1976 based on medium-scale integrated circuit PCM technology. LPCM is used for the lossless encoding of audio data in the compact disc Red Book standard, introduced in 1982. AES-3 is a particular format using LPCM. On PCs, Pcm and LPCM often refer to the format used in WAV and AIFF audio container formats. LPCM data may also be stored in other formats such as AU, raw audio format and various multimedia container formats. LPCM has been defined as a part of the DVD and Blu-ray standards. It is also defined as a part of various digital video and audio storage formats. LPCM is used by HDMI, a single-cable digital audio-video connector interface for transmitting uncompressed digital data. RF64 container format uses LPCM and also allows non-PCM bitstream storage. Various compression formats contained in the RF64 file as data bursts can be disguised as Pcm linear modulation. In the diagram, a sine wave is sampled and quantized for Pcm. The sine wave is sampled at regular intervals, shown as vertical lines. For each sample, one of the available values is chosen by some algorithm. This produces a fully discrete representation of the input signal that can be easily encoded as digital data for storage or manipulation. For the sine wave example at right, we can verify that the quantized values at the sampling moments are 8, 9, 11, 13, 14, 15, 15, 15, 14, etc. Encoding these values as binary numbers would result in the following set of nibbles: 1000, 1001, 1011, 1101, 1110, 1111, 1111, 1111, 1110, etc. These digital values could then be further processed or analyzed by a digital signal processor. Several PCM streams could also be multiplexed into a larger aggregate data stream, generally for transmission of multiple streams over a single physical link. One technique is called time division multiplexing and is widely used, notably in the modern public telephone system. The PCM process is commonly implemented on a single integrated circuit generally referred to as an analog-to-digital converter. Demodulation: to recover the original signal from the sampled data, a demodulator can apply the procedure of modulation in reverse. After each sampling period, the demodulator reads the next value and shifts the output signal to the new value. As a result of these transitions, the signal has a significant amount of high-frequency energy caused by aliasing. To remove these undesirable frequencies and leave the original signal, the demodulator passes the signal through analog filters that suppress energy outside the expected frequency range. The sampling theorem shows PCM devices can operate without introducing distortions within their designed frequency bands if they provide a sampling frequency twice that of the input signal. For example, in telephony, the usable voice frequency band ranges from approximately 300 Hz to 3400 Hz. Therefore, per the Newista-Shannon sampling theorem, the sampling frequency must be at least twice the voice frequency for effective reconstruction of the voice signal. The electronics involved in producing an accurate analog signal from the discrete data are similar to those used for generating the digital signal. These devices are digital-to-analog converters. They produce a voltage or current that represents the value presented on their digital inputs. This output would then generally be filtered and amplified for use. Standard sampling resolutions and rates: common sample resolutions for LPCM are 8, 16, 20 or 24 bits per sample. LPCM encodes a single sound channel. Support for multi-channel audio depends on file format and relies on interweaving or synchronization of LPCM streams. While 2 channels is the most common format, some can support up to 8 audio channels. Common sampling frequencies are 48 kHz as used with DVD format videos, or 44.1 kHz as used in compact discs. Sampling frequencies of 96 kHz or 192 kHz can be used on some newer equipment, with the higher value equating to 6.144 megabit per second for 2 channels at 16 bit per sample value, but the benefits have been debated. The bit rate limit for LPCM audio on DVD video is also 6.144 bits, allowing 8 channels a 48 kHz a 16 bit per sample equals 6144 kbits. There is a L32-bit PCM, and there are many sound cards that support it. Limitations: there are potential sources of impairment implicit in any PCM system. Choosing a discrete value that is near but not exactly at the analog signal level for each sample leads to quantization error. Between samples no measurement of the signal is made. The sampling theorem guarantees non-ambiguous representation and recovery of the signal only if it has no energy at frequency fs/2 or higher. Higher frequencies will generally not be correctly represented or recovered. As samples are dependent on time, an accurate clock is required for accurate reproduction. If either the encoding or decoding clock is not stable, its frequency drift will directly affect the output quality of the device. Digitization as part of the PCM process: in conventional PCM, the analog signal may be processed before being digitized. Once the signal is digitized, the PCM signal is usually subjected to further processing. PCM with linear quantization is known as linear PCM. Some forms of PCM combine signal processing with coding. Older versions of these systems applied of the processing in the analog domain as part of the analog-to-digital process. Newer implementations do so in the digital domain. These simple techniques have been largely rendered obsolete by modern transform-based audio compression techniques. Dpcm encodes the PCM values as differences between the current and the predicted value. An algorithm predicts the next sample based on the previous samples, and the encoder stores only the difference between this prediction and the actual value. If the prediction is reasonable, fewer bits can be used to represent the same information. For audio, this type of encoding reduces the number of bits required per sample by about 25% compared to PCM. Adaptive Dpcm is a variant of Dpcm that varies the size of the quantization step, to allow further reduction of the required bandwidth for a given signal-to-noise ratio. Delta modulation is a form of Dpcm which uses 1 bit per sample. In telephony, a standard audio signal for a single phone call is encoded as 8,000 analog samples per second, of 8 bits each, giving a 64 kbits digital signal known as DSO. The default signal compression encoding on a DSO is either a 1/4 LPCM or a LPCM. These are logarithmic compression systems where a 12 or 13-bit linear PCM sample number is mapped into an 8-bit value. This system is described by International Standard G711. An alternative proposal for a floating-point representation, with 5-bit mantissa and 3-bit radix, was abandoned. Where circuit costs are high and loss of voice quality is acceptable, it sometimes makes sense to compress the voice signal even further. An ADPCM algorithm is used to map a series of 8-bit micron law or a law PCM samples into a series of 4-bit ADPCM samples. In this way, the capacity of the line is doubled. The technique is detailed in the G726 standard. Later it was found that even further compression was possible and additional standards were published. Some of these international standards describe systems and ideas which are covered by privately owned patents, and thus use of these standards requires payments to the patent holders. Some ADPCM techniques are used in voice-over IP communications. Encoding for serial transmission. PCM can be either return to zero or non-return to zero. For a NRZ system to be synchronized using in-band information, there must not be long sequences of identical symbols, such as ones or zeros. For binary PCM systems, the density of one symbols is called one's density. One's density is often controlled using precoding techniques such as run-length limited encoding, where the PCM code is expanded into a slightly longer code with a guaranteed bound on one's density before modulation into the channel. In other cases, extra framing bits are added into the stream which guarantee at least occasional symbol transitions. Another technique used to control one's density is the use of a Scrambler Polynomial on the raw data, which will tend to turn the raw data stream into a stream that looks pseudo-random, but where the raw stream can be recovered exactly by reversing the effect of the polynomial. In this case, long runs of zeros or ones are still possible on the output, but are considered unlikely enough to be within normal engineering tolerance. In other cases, the long-term DC value of the modulated signal is important, as building up a DC offset will tend to bias detector circuits out of their operating range. In this case, special measures are taken to keep account of the cumulative DC offset, and to modify the codes if necessary to make the DC offset always tend back to zero. Many of these codes are bipolar codes, where the pulses can be positive, negative or absent. In the typical alternate mark conversion code, non-zero pulses alternate between being positive and negative. These rules may be violated to generate special symbols used for framing or other special purposes. Nomenclature: the word pulse in the term pulse code modulation refers to the pulses to be found in the transmission line. This perhaps is a natural consequence of this technique having evolved alongside two analog methods, pulse width modulation and pulse position modulation, in which the information to be encoded is in fact represented by discrete signal pulses of varying width or position, respectively. In this respect, PCM bears little resemblance to these other forms of signal encoding, except that all can be used in time division multiplexing, and the numbers of the PCM codes are represented as electrical pulses. The device that performs the coding and decoding function in a telephone circuit is called a codec. See also, AES-3, beta encoder, equivalent pulse code modulation noise, G711 a TUT standard for audio companding. It is primarily used in telephony. Newest Shannon's sampling theorem, pulse density modulation, quantization, sampling, signal to quantization noise ratio a 1 method of measuring quantization error. Notes. References. Further reading, Franklin S. Cooper. Ignatius Mattingly. Computer-controlled PCM system for investigation of dichotic speech perception. Journal of the Acoustical Society of America 46, 115 doi, 10.1121/1.19726888. Ken C. Pullman. Principles of Digital Audio. Carmel, Indiana, Sam's Prentice Hall Computer Publishing. ISBN A0-672-22634-0. D. H. Hallen, E. O. Wiley, Philip E. Rubin, and Franklin S. Cooper. The Haskins Laboratories Pulse Code Modulation System. Behavior Research Methods, Instruments, and Computers 22, 550 a 559 doi, 10.3758/BF03204440. Bill Wagner. Pulse Code Modulation Techniques. New York, New York, Van Nostrand Reinhold. ISBN A0-442-01436-8. Bill Wagner. Pulse Code Modulation Systems Design. Boston, Massachusetts, Artec House. ISBN A0-89006-776-7. External links. PCM description on multimedia wiki. Ralph Miller and Bob Badgerly invented multi-level PCM independently in their work at Bell Labs on Sixily, U.S. Patent 3,912,868 filed in 1943, ENA pulse code modulation. Information about PCM, a description of PCM with links to information about subtypes of this format, and references to their specifications. Summary of LPCM contains links to information about implementations and their specifications. How to control internal-external hardware using Microsoft's Media Control Interface contains information about, and specifications for the implementation of LPCM used in WAV files. RFC 4856 a Euro-media type registration of payload formats in the RTP profile for audio and video conferences a Euro Audio L8 and Audio L16, RFC 3190 a Euro RTP payload format for 12-bit DAT audio and 20 and 24-bit linear sampled audio, RFC 3551 a Euro RTP profile for audio and video conferences with minimal control a Euro L8 and L16.